Hi, everybody. Thanks for coming. Just curious, has anybody of you been to Björn Fahler's talk about type-safe C++? Bunch of people. So I find the theme kind of interesting that actually most of the C++ talks at this conference have been one way or the other concerned with type safety. So apparently this seems to be quite a big deal for us C++ programmers, and my talk is no exception. But what you will notice is, if you've been to Björn's talk, that it approaches the issue from a different angle. So there's quite apparently a lot of different perspectives on this, and mine is just one of them. So that's a small disclaimer in the beginning. Quick introduction about who I am. I'm a freelancer working in Berlin, Germany, working on firmware development for embedded systems. And what I consider to be my mission here is to combine or to bring type safety to low-level development. Because I always found it quite baffling that we work very close to the hardware and just write our programs in a very imperative style without taking a lot of care to making sure that the commands that we send directly to hardware, we don't take a lot of steps to actually make sure that they are correct. And type safety has a lot of potential to making sure that things that we send to hardware actually are consistent, make sense, and ultimately do the correct thing. So combining these things is really what I focus on, what I kind of research into, so to speak. I have a couple of side projects. These are the topic of my talk, which is about game console emulation. If you've ever tried to play a Sony PSP, a Nintendo GameCube, Wii, or Nintendo 3DS game on your computer, for instance, you will probably have seen one of these icons. And these are projects that I contributed to on the small scale as well as on the large scale. So I've been doing that for about 5 to 8 years, depending on how you count it. So there's really a lot of interesting stuff to learn about that. And if you're looking for an interesting side project to learn about computer architecture, for instance, definitely recommend checking out the emulation scene. I regularly post on this stuff on Twitter. My projects are all public, and I have a website with a blog. So if you want to learn more, feel free to check those out as well. Right. What is this about? Surprisingly, perhaps, it's about serialization and emulation. It's actually about type safety, but they are linked together, as we will see in a minute. But serialization turns out to be quite the significant problem in emulation. I will show you a couple of examples about where it shows up, what kind of issues we have with a naive approach. And one specific example will be the inter-process communication subsystem of the Nintendo 3DS. Again, we will see what kind of issues arise, what do we actually want to address, and how do we address it. And specifically, our tool of choice here, well, and generative and declarative are two approaches I found quite useful in this case. A tool of use for this is modern C++. Modern C++ will help us reduce a lot of boilerplate in our code. We want to mostly automate all of the annoying things like keeping count of offsets, making sure that our types match the actual data that we serialize, and other things like that. And during all of this automation, we do not want to forget that all the inputs that we have need to be validated properly. So inputs that are supposed to be positive should not be negative, obviously, otherwise it's an error. Strings that should not be empty, obviously. But we all need to check for that, and it's easy when automating things to just say, okay, we automate this, and well, then we just don't validate our inputs. But we want all of it. We want to have our cake and eat it. And finally, we want to maximize reuse throughout this entire discussion. That is about the last third of my talk, where we will see how that can be achieved. As a small note about what modern C++ actually means here, we're talking about C++ 11 with some C++ 17 features. That said, does that work? It does work. That said, all of the things I will show you can technically be implemented with older C++ standards like C++ 98. The difference is the implementation will actually fit on the slides, and for those of you who might not have too much C++ experience, you will actually understand what I'm talking about. Whereas with the C++ 98 solution, you probably wouldn't understand it because it would, fill a book or something. Right. Speaking of that, small digression in the beginning, I want to get a little bit of an idea of where my audience is actually standing at. So can everybody raise their hands when they work with C++ or at least regularly use it in side projects, for instance? That's quite a few hands and quite a few non-hands as well. Of those of you who use C++, do you use modern C++, C++ 11 or beyond? So that's almost the same group, interesting. And finally, how many of you do work on low-level software, like compilers, kernels, firmwares, or anything close to the hardware, really? So that's significantly fewer hands, interesting. If you're in one of the groups who never raised their hand at all now, don't worry. Hopefully the code on the slides will be clear enough that you'll be able to take away at least the core statements and the core ideas of what I'm talking about. If you're in the group that, well, that doesn't work, that doesn't use C++ 11, don't despair either. Consider this more of a tour of modern C++ features then. And if you've never worked with low-level software, well, this is a good opportunity to get to know what kind of problems we're tackling here. Right. That said, that's all my questions for you, and now it's your turn. If at any point you have a question, feel free to interrupt me. If I'm not seeing you, just shout at me, yell at me, whatever. I'm happy with that. And yeah, I feel like any question does contribute to the talk, so even if you just want to clarify, have some C++ feature clarified, do not hesitate to ask. Right, so let's dive right in. Emulation and serialization. And to give you an idea of why that's a big deal, I gave you a small overview here about what the typical high-level software piece looks like. On the left side here, we have two CPU-side modules, threads for instance, communicating with some sort of hardware and with an operating system. It's rather abstract. How does it look like in a game, for instance? Well, we might have a main application thread right here, which is responsible for rendering things or for doing the physics calculations, things like that, as well as a scripting engine on the bottom left here. And both of these might be interacting with the host GPU and with an operating system. And how does it actually look like when they try to interact? Well, for the main thread, it's trivial, right? You just have two application threads, and how does one interact with the other? Well, they just call a C++ function and pass in some arguments, and that gets the job done. We want to do a system call, for instance, to read a file. You have a similar kind of thing. You have a C interface, and you just call a function, and it's slightly more involved because you need to make sure that your arguments are passed in the right way, because the kernel expects it to be in some certain order. But that also is hidden away from you mostly, so it's a thing of calling conventions, and the compiler just decorates system calls with the right calling convention and just takes care of it for you. The only kind of non-trivial thing to do for the programmer is when they want to interact with the GPU driver, for instance, and in that case, they kind of just copy memory around. They copy some vertex data or command buffer data into a GPU driver visible memory chunk, and that's all there is to it. So it's not a function call, but it's still relatively simple. Now let's look at it, how it looks like from an emulator's perspective that emulates a given game. So all of the modules that we had previously now become virtualized. So we have a virtualized CPU communicating with a virtualized GPU. So say this one wanted to just kick off some rendering commands, but we don't really know anything about that. What we see is just the virtual CPU writing to this large pool in the middle here, which is main memory. So it just sends some, U8 32-bit writes, for instance, to main memory, and we don't know anything about that data until it actually triggers some sort of operation. So that's why I like to call this chunk of main memory the untyped C of raw data, because it's really just a bunch of bits and bytes, and we don't know any of their meaning until, well, they are already being used for something. And when that happens, what we need to do on the emulator side is we need to deserialize this data. So we need to take the ones and zeros and somehow reintroduce the type structure on top of it to make sense of it. For instance, if we have a vertex buffer, we need to turn all of the raw U8 data into floating point formats, for instance. So that's possibly deserialization in a more broader sense, but certainly still deserialization. And similarly, the operating system, when doing system calls, needs to turn CPU registers into well-formed arguments, because CPU registers are just 32-bit values. Some of them might be just that. It might be a 32-bit size, but some of them might need to be grouped together to form a 64-bit value, for instance. So that kind of stuff needs to be taken care of. And this is really, really a quite ubiquitous problem in emulation. So there are a couple of examples are listed here, and the common theme is we want to take this untyped data and turn it into some sort of high-level C++ element, so to speak. And the first example is the system calls, where we take CPU registers and forward them to a C++ function. Another example might be inter-process communication, as we'll see later, which turns main memory into a C++ function call. Or we might have some sort of emulated file I/O, where we read something from disk and we want to turn it into, well, a BMP header, for instance. Who knows? And this is kind of a standard so the file I/O thing is a standard problem that you see in many cases. Emulation has the interesting twist that often we need to do endian as swapping on our inputs, because the emulated platform might be big endian, like for the Nintendo Wii, for instance, whereas hosts tend to be little endian, unless you actually emulate on the Wii, which is an interesting problem because, yeah. Right, and finally, the GPU command buffer example I showed in the previous slide. Yeah, and the question that I want to address in this talk is, given that this is such a ubiquitous problem, and we want to do it reliably and without boilerplate, how can we do this reliably? So, without boilerplate, because boilerplate causes issues, because at some point when we keep track of offsets, we are bound to mess up eventually. We want to validate inputs consistently, and we want to, again, as mentioned before, and we want to detect invalid system states. What I mean with that specifically is, if we have a kernel object file handle, and that is used for a file reading operation, we can probably be quite certain that it's going to be a file handle, just because it's used for file operations. But now if the application uses this file handle 2 seconds later for a synchronization operation as a mutex, then clearly something must be wrong, because a file is not a mutex. So this can be multiple things, really. It could be a CPU emulation bug. Some arithmetic was returning the wrong result, so accidentally the handle wasn't incremented properly. Or maybe, I don't know, some of our emulated kernel was overwriting data and just accidentally, whatever. And the really key thing here is that in emulation we don't have a lot of debugging devices, so we want to detect these kind of states as early as possible at all, because we want really to take all the debugging devices we can possibly have. Right, and today's goal is we're going to address all of these issues for one specific example, and we want to let the compiler do it, because they will have all the information they need, and will save us a lot of development and debugging time. An example of this, just to give you a quick concrete example, is something I presented at C++ London back in February. And this is the system call example I alluded at before, on ARM32 specifically, which is the architecture used on the Nintendo 3DS. The way this works is that there are a couple of system calls, about 100 of them, and for instance, this is a DMA operation. DMA is just a fancy way of copying memory around, basically, using dedicated hardware, but ultimately just copying memory around. And the application will prepare some sort of parameter values into the virtualized CPU registers, and then it will call an SVC instruction. SVC is just the thing that triggers a system call. It gets a number, in this case 0x55, which determines which operation to do. So a DMA in this case. And what we want to do in an emulator is we want to ultimately call some function called svc start DMA, which implements all of the DMA operations. We somehow need to get the values from over here into that function call. Now, it sounds like an easy problem, but there are two twists on this. First one is you don't just blindly copy over the values, but for some of them you need to do special things. And specifically when kernel objects are being referenced, like process handles or file handles, you need to do some sort of lookup process first. So you don't want to copy the values over verbatimly, but want to wrap them in a lookup function. It's the first twist. That would be manageable. The more important twist is that the parameter order, the parameter order doesn't actually match the register order. So if you look closely, you will see that the first argument here, the 5, is taken from register 1 rather than register 0, then goes on to register 2, register 3, and then, weirdly enough, it jumps back to register 0, only to jump back to register 4 again. So that's big fun. And you can imagine, given that there are 100 system calls like these, and all of them follow a similar pattern, but slightly different register orders, it's incredibly easy to mess this kind of order up, and that is why we really want to automate this process as far as possible. Right, and if you're interested, I will put up the slides after the talk, and you can click the link and follow it, or you just look it up on the internet, whatever. But yeah, this talk, as I was saying before, will be concerned about the inter-process communication subsystem instead. And to do that, I will first give you a quick overview about the Nintendo 3DS and what it looks like. So it's Nintendo's current handheld generation, depending on how you define handheld, I suppose, because the Nintendo Switch has come out since. It was released back in 2011, so it has had quite the lifespan for this kind of industry. I like to refer to it as a big embedded system because it's comparable to smartphones at the time of its release. It boasts 2 CPU cores clocked at about 300 megahertz. It has a dedicated GPU, which is quite unique. I'm not aware of any other products that actually use the PK200 in the Western market anyway. And it has relatively large amounts of RAM as well. So that is reflected in the software stack. It's not running a kind of custom-ish Linux kernel like your desktop PC or laptop might be running, but neither are the games running on bare metal. So there's actually a kernel on the system, a microkernel, which provides functionality for synchronization, memory management, access restriction, things like that. So that's really just the bare minimum of a kernel, so to speak, and all the interesting functionality like GPU drivers, audio playback, or file system access, that is hidden behind separate processes on the system, microservices, so to speak. So if the game wants to do anything interesting, they always communicate with these separate processes, and that's how anything interesting is done on the system. If you look at this as a kind of stack, we see at the very bottom we have our hardware, the ARM11 CPUs. And in the emulator, what we do for this is we just go through each instruction one by one. We have a block of virtual CPU registers, and we just call a C++ function corresponding to the functionality of the current instruction, then move on to the next instruction. So if we wanted to add 2 registers together, we just read them from our register block, add them together, store the result again in the register block, and move on. That's at least the simple idea. If you want to be fancy, it gets more complicated, but this model suffices for our talk. At the very top, you have the game, or the browser if you fancy using that on the 3DS, which just runs on the emulated CPU. We just load the game's binary and throw our emulated CPU on it, and it just magically does its thing, so that's great. But what's interesting is that every now and then this game will call some sort of system call, so we get an additional layer in the system, which is the kernel. Now, we could do a similar thing for the game, where we just run the kernel's image directly on the emulated CPU, but the system call interface is actually well-defined enough that we can just high-level emulate this, is what we call it. So we just, for each system call, have a C++ function that re-implements that functionality directly. And in between, we have the services. Again, we could just load their images, and they would be relatively lightweight to emulate, but we can just implement their interfaces directly as well. So that's easy enough as well. So the interface between the game and the kernel is what I presented at C++ London, and the interface between the game and the services, which is actually more interesting. This is what I'm presenting today. So hopefully that spikes your interest a little. Right, and inter-process communication, what does it look like? Well, first of all, why is it crucial? As I've been mentioning before, to do anything interesting on the system, you need inter-process communication because the interesting functionality is provided in different processes. So there's one process dedicated to rendering graphics, it's called GSP, one for audio, it has a different name, one for Wi-Fi, one for connecting to social media, something for accessing the file system, whether that's for loading assets or for saving a game's progress. And overall, there are 40 different processes like this on the system, each of which is serving different kinds of functionality. And the protocol they use for communicating here is kind of client-server architecture, so the game being the client and the services being servers, which seems reasonable. And when they want to communicate, they do so using a request-response protocol. So the game will craft some sort of memory block in which it has a kind of command header and a couple of parameters, so a couple of arguments, and it will send that off to the server, to the services, which then know their functionality. And once that's done, they craft a response block and send that back to the application. This communication is not done directly, but it's marshaled through the kernel in case any sensitive data needs to be sanitized, or if any memory pointers, for instance, need to be translated across address spaces, things like that. Yeah, there is some sort of hierarchy as well, which is kind of a side detail. So there are two classes of processes, of microservices, high-level ones and low-level ones. And the game only has access to the high-level ones, whereas the low-level ones are concerned with things like power management or direct hardware access, which you kind of want to isolate from the game for security purposes. So it's quite interesting how that architecture is not only used for separation of concerns, but also for security in a sense. Right, so how does it look in practice? I'm sure you're eager to actually see a concrete particular example. This is an example of a read file operation triggered by an application like a game or the browser. The common theme here is that at the top, so this has 8 32-bit values in here in the command block. It has a command header at the top, which gives us 3 pieces of information that are encoded in this 32-bit value. The upper 16-bit, right here, this 802, tells us which kind of operation to execute. So this is the part that tells us, hey, I want to read a file, as opposed to writing a file, closing a file, or whatever. The lower 8 bits here tell us how many parameters to expect, and specifically how many regular value parameters to expect, which are these 5 ones down here. And then the 8 bits in the middle tell us how many extra parameters follow that need some sort of special translation process, whatever that means. So you can see we have 5 normal parameters, 2 translation parameters, and that matches the number of arguments that actually follow in this block. And to see how this translation process looks like, I've prepared a little animation which hopefully works now. Yeah. So we can see this thing is sent off to the kernel, and the kernel will then begin going through the parameters one by one and copy it to an intermediate staging buffer. Animation is playing too fast. We'll copy it to an intermediate staging buffer verbatimly, and for these two it will do some sort of translation process, as you see in a minute. And once that is done, the kernel will hand the operation off to the servers, which then does some processing indicated by the small gear here. And then, the process kind of begins in reverse again. So the service has done its processing, has gathered the results, and will craft another command block like this that gives sends it to the kernel does the translation process again, and then sends it back to the application. Right, and at the bottom here, you will see that this, let's use the pointer. It could be a buffer address, for instance. This buffer address is different on the right side here. So in this case, if you wanted to map a buffer into the target process, the kernel would take care of that for you, and this is why the virtual memory address would be a different one. Right, so given this kind of, and to be clear, where our emulator comes into play is the small spinning gear, so to speak. So the subsystem we talk about today only gets this translated buffer and wants to do something with it. So the question is now, how do we implement this spinning gear? Well, this is shown on the next slide. There is a common dispatch kind of flow. So we first look at the command ID given in the command header and select some high-level C++ function that we want to use to implement this functionality. In this case, we might have a function called doReadFile, taking something like a 32-bit file descriptor, a file offset, 64-bit, a number of bytes to read from the file at that offset, and a pointer to emulated memory. So it's not a proper pointer in C++ because it's emulated memory, so it gets its own type in our case. It might do its operation and then return two results. We do this in C++ using what we call a tuple. So it returns a result, which is usually 0 to indicate success, and a uint32 that would give us, for instance, the number of bytes that we actually read from the file. Once we select this handler function, we haven't actually called it yet. We still need to make sure that we can actually call it and need to figure out how. So the first thing we do is we verify the command header to make sure that, for instance, the application isn't sending us this read file command ID, but doesn't actually send any parameters, because that would be malformed. We want to catch these kind of cases in the spirit of input validation. So don't worry about this expression too much. It's just what it is, basically. Very simple arithmetic. And once that seems legitimate, we pass the command buffer and go through each of the elements one by one and, well, do the deserialization process, basically. The twist here is that for some of these objects, so the uint32 here is just the uint32 in the function that is being called, so we just take it. But the next parameter that we expect was a uint64. So we want to pass two values, these two, and stitch them together to form a 64-bit value from two 32-bit values. And similarly for the next one, and then for the final one, we get this kind of buffer descriptor. So you've seen there two entries before, and they also belong together to form a single buffer address. Don't worry about the buffer descriptor too much, just want to highlight that it exists, and they kind of need to be considered as a single entity rather than separately. And once we do that, we can finally invoke our C++ handler function with the properly decoded arguments, get the result, and then we need to write back the response header to the command block. So that's kind of the reverse process again. So we have a command header again, but a different number of response arguments. First one would just be our success code, 0, and the number of bytes read, which would be 0xD00F in our case. Next question over there. Pardon, could you speak up a little?
Sorry. The bytes to read is a 64-bit value, right? In that first function there?
Yeah.
And then the bytes read are 32-bit.
Yeah, I messed up the slides on that one.
Okay.
So the remark from the old...
Something platform-specific there.
Right. So the remark has been that we take a 64-bit value for the number of bytes read and return a 32-bit value for the number of bytes read, ironically. So I was responding that it might be a mess up on my slides. I'm not actually sure it is. It might as well just be an oddity of the system as well. Because quite frankly, none of the files on the system are large enough to warrant the use of 64-bit integers. So I'm not really sure why they would use that. Right, thanks for the question. Yeah. Now the question is, this is a relatively easy slide. You know, all of the logic we need to do fits in 5 points, so to speak. So you might say, hey, that's not actually that bad. Well, now consider, however, there are 40 active processes on the system. And each of these processes has about 30 different IPC commands in total. So each of these requires different manual glue. So this 5-step process, you know, these are 3 lines of code, but this blows up to quite a significant amount of code if you actually translate it to C++. So do that like about 1,200 times, and you spend a lot of time doing that. So that's a lot of work. Specifically, I would like to highlight the file system service, which isn't just 30 commands. It's a lot. So each of the lines in this table is an IPC command. And there are a lot of them. And now imagine you needed to implement this kind of 5-step process for each of those. You certainly don't want to do that if you can help it. So yeah, it's a lot of work, or is it? So that is where we want to enter a technique I call generative programming. Well, Not only I call it like that, it's quite the accepted idiom in the community. And there are a couple of building blocks to this. So ultimately what we want to do, there's a nice graphic here, is we have what we call type lists, which are quite a common metaprogramming device. And we want to run generators on it, which basically allow us to evaluate a particular kind of expression on each of the elements of a type list. For instance, the type list could be a list of, who knows, types in a command block, and the operation could be to decode the values from a command block, which might be precisely what we do later. So using these generators, we can turn type lists, which are purely a type system entity, and turn them into runtime code to automate things, basically. Now the question is, how do we actually get type lists? Well, we can generate them directly from our functions using limited reflection capabilities in our language. So what that looks like specifically, this is, so to speak, the vision that I want to present for the rest of the talk now, is we start at this function, we look closely and observe, hey, this function actually has all the information we need. It doesn't have the command ID, but it does tell us it takes a uint32, a uint64, which needs 2 u32 values. Another u64, so that's another 2 command block entries, and this writable buffer, sorry, I renamed the type on the slide, but it's the same as before. You know, it takes this buffer descriptor and the buffer address, so again, 2 command buffer entries. And it returns 2 values in the response command block. So really, in terms of the command block, we know everything we need to know to handle the command properly just from the signature itself. Now, the function signature itself is not something we can do anything with. We just call functions usually. But there's a thing called function traits in C++. It's not a standard library feature or anything, but we can implement it reasonably easy. And what this will do is it will turn this function signature into 2 type lists containing basically the input parameters, so u32, u64, 64, and the writable buffer, and the response lists. And if we get that, we can actually do regular template metaprogramming. Don't worry if you don't have any experience with that, by the way. But we can throw well-known techniques on this and write our generators that do this kind of runtime code generation later on for us. And once we have done that, we can combine it all together. And well, quite frankly, I still, every time I give this talk, I find this quite amazing. Basically, this, where was it? Yeah, this 5-step process, we all reduce it to this single line of code. And it's just entirely reusable for all the command handlers in our system. So instead of do read file, we could put do close file, do open file, and all of the thing files together. And they are all handled by the single function, and it will just deduce all of the necessary operations to be done from the function signature. So in terms of automation, this is as good as it gets, really. So yeah, advantages, it's all automated. There's no room for possible typos or mental arithmetic errors anymore. It's type safe because decoded data matches the C++ function signature by design. There is no way we could decode a uint32 value, for instance, and accidentally pass it to a 64-bit parameter by implicit conversion, for instance, because it will always take a 64-bit value if the parameter was 64-bit. And that's by design, really, which is always a good thing to say. And a bonus, it's easier to read because, well, there's nothing to read anymore. It's just that single line of code, so anybody looking at that code would have an easy time understanding what it does. Right, so the rest of the talk will basically be concerned with how we implement this. So function traits, if you're not familiar with the term traits, it comes from the type traits that we have, which give us information about a particular type. So we can ask C++, hey, is this type a pointer? Is it an integral value? Is it a floating point? Things like that. If you apply this concept to functions, this is just what a function trait is. And specifically, what we're interested in is getting the parameter list and the return type. So in other words, we want a C++ structure, template structure, taking the function type. It has 2 members. But these aren't data members or anything, but they are types of their own. So we get one type def arguments, which is just a type list of the parameters of the given functions. So this might be our U32, U64, U64 writable buffer list from before. And similarly, we get a result type def in the function trait that tells us what the return type of the function is. So that would be our result and the number of bytes written. But not the actual values, but just the types. Right. Implementing this can be quite cumbersome. So that's why I recommend using either of the two libraries listed on the slide here. At least one of them actually has a standalone version as well if you don't fancy using Boost for any particular reason. For our case, actually implementing them will be really, really easy because we have a very specific kind of functions, namely just free functions. And you can just implement it using this code. I will not go into detail about how it works, but I found it quite interesting to know that such a powerful device actually can be implemented in, 7 lines of code or so, as opposed to 200 lines of code. And this actually works perfectly fine for our purpose. There's no gotchas. Right. Now, the core idea that we have is we want to take the type lists we get from function traits and want to turn them into runtime code. Well, how do we do that? There are kind of two legacy approaches to this. One being recursion, so you take the front type of the first type of the type list, execute the operation on it, then drop it off the list and recurse into the tail of the function, in the tail of the type list. The other one might be to use a old-style metaprogramming library like Boost MPL or Boost HANA. But the newer approaches, so to speak, are parameter pack expansions, which are based on variadic templates, which are a lot of very important words. If you've never heard about them, we'll see about it in a minute. Another one being fault expressions. So these two features allow you to do the same thing as recursion and this for each thing in a very concise and very intuitive manner as well. So that's quite a big win in terms of how modern C++ enriches the style of programming that we use. Right. So this is what we'll actually do now. How do we generate this code? Well, to clarify again, we get this kind of type list, which is just the arguments of our function, which we got from function traits. And we've had this kind of command block that we want to read the values from. Well, let's start very small. Let's suppose we had some sort of primitive, a decode entry function that takes a given type and an offset. So this would be 1, 2, 3, just counting into the command buffer. And at that offset in the buffer, it will decode a value of the given type. So in this case, it would just get the UN32, but in this case, it would actually pass two entries from the command buffer and stitch them together. And then once that is done, so this is taken by reference, so it will increment the offset automatically for us. So we can just call the decode entry function multiple times with different types to step through the command buffer and decode all the results. So I will show the implementation of this function in the next slide, but assuming we already have it, what can we do? We can now write a function decode all, which is a variadic template function. What that means is it takes multiple types, which we indicate by these triple dots, takes any number of types that you want to pass it to. As a regular function parameter, it just takes the command block. In the function implementation, we keep an offset parameter starting at 1, which skips the command header, so starting at the first actual entry of the buffer. And then we do this. So ignoring all the weird stuff around this, what we do is we just call the decode entry function at the type, at the current type, at the current offset, at the command block. Now what we do is we put 3 dots after this expression. And this is what we call a parameter pack expansion. And what this will do is it will take this expression and duplicate it for each of the parameters that were passed to the function template. So if we give this type list, this will expand to something like decode entry UN32, so-and-so, comma, decode entry UN64, so-and-so, comma, and the same for the other 64-bit value and the writable buffer. Now, that is not quite what we want yet, but it's the largest part of it. Now, the only thing we want to do is we will actually want to apply the decoded arguments to a function, which is precisely our handler for the RPC command. It's do read file. So do read file just gets the decoded results directly inserted into the function call, so that the arguments will just be there. The function call will stitch them together and return the result from the handler. So this faded in a lot of stuff, but ultimately that's just all I did there. I just added the function call. And you need a new template argument, function argument, and stuff. But it's really not a big deal. Right. Yeah, really value-added templates and parameter packs are awesome for this kind of thing, because I haven't shown you this decode entry function yet, but naively you might have expected that actually iterating over the entire command block might require some sort of for loop, some more advanced index counting or anything. But no, really it's all boils down to this parameter pack expansion at the bottom right here. So that's really, really powerful. Now, if we actually want to see how decode entry is implemented, you could start specializing your function for each of the different types that we might have. But there's actually in C++ 17 an easier feature to do so, and that's called const exper if. So what const exper if does, if you're confused about it, actually ignore the const exper for now and just pretend this is an if. We have an if check that checks using a type trait is same v, whether t is a uint32-bit value. If it is, then we know, okay, we just return the value at the current block offset, and post increment the offset. I just return the previous value from the function. So that's easy. If that is not the case, well, we do other stuff. Now, let's say, so that is really all we need for 32-bit values. Say we had a 64-bit value. Well, we won't hit this case, but we might hit the next case with 64-bit values. And again, it's really relatively easy. We just take the first value and the second value, increment the offset after reading each, and stitch them together and return that. Again, relatively easy. Suppose we had a different one. Well, if it's a writable buffer, we just read the descriptor. We do some sort of more advanced logic here because we need to decode the descriptor first, which I will not bore you with, but it might return you some sort of size, for instance. And then you get the address and construct a writable buffer object from the address and the size. In this case, we just ignore the flags. Right. Now, I told you to ignore const exper if for now. Well, what the const exper does, it actually makes sure that if this is not a uint32, it just ignores whatever is inside of here. You need to do that to actually be able to rely on the type being 32-bit. So in this case, why you need to do that is because these three branches have different return types, but you always want to actually return the type of your respective branch. And that is always determined by the type passed to the function. So really, this is quite a concise and neat way to specialize a function easily for different types. It's in C++ 17, so it requires relatively modern compiler support, but if you can use it, it's really, really nice. Right, to get back to the full example here, now that you've seen this, again, we have our decode all and apply function. Just use a parameter pack expansion to step through the entire buffer, blue, red, yellow, green, one by one, and gather results and call the function handler for that. Now, there are two caveats with this. First one is, well, first of all, there's no boilerplate, which is always nice. But there are two caveats. The first one is this is actually not a variadic template. What we actually need is to pass a single template parameter, which is a std tuple with the given type list. I won't go into details about how to solve that. Basically, it's a standard problem, really, and just a technical one. You turn the function into a function object, which is a structure that has a function call operator, and it gets complicated, but really it's a standard technique if you run into this kind of issue, and I don't want to bore you with that. The more interesting caveat, however, is the handler right here. So we have a function call with the given arguments. And this is a decode, like this steps through the buffer one by one, incrementing the offset each time. So we really depend on this being executed in sequence. We wouldn't want the compiler to start evaluating the decode entry of the writable buffer thing first, because at that point offset is still 1, and it would decode the wrong thing. So really we want to enforce the compiler to start at uint32, but the issue is that in function calls, expression order is not well specified in the C++ standard. It's just left to the implementation which order to evaluate things in. That's something you need to take care of, and there are tricks to get around it. Initializer list is a common keyword in that aspect. I don't want to go into detail about how to resolve that specifically, because we're kind of running short of time already. But I just wanted to highlight the issue. So don't verbatimly copy this code, please, before worrying about that issue. Right, time for a quick demo, just so you see how this looks like in practice. And so you get to see a little bit more code, and maybe we can do weird stuff with our desktop. Again, forgot to adapt the color scheme for the presentation, unfortunately, but I hope you can still read it. As a font beginner for everybody. All right, cool. So there's not a lot to talk about here, really. You can see similar structures as we've seen before. This is just a dummy kind of environment with a command block that is just a couple of 32-bit values. And just boilerplate code, etc. But here is the actual function we've seen before, decode and all and apply, with slightly different names, I believe, but oh well. And you can see we're using the if const exper cascade here to decode a single entry, and then again use a parameter pack expansion to decode the entire buffer in one go. And what I'm using here is this call with sequential evaluation trick, which basically constructs an object, the sole purpose of which is to call this function f, could be do read file in our case, with the sequentially evaluated arguments given on the right-hand side of the expression. So that's quite a neat trick I found to actually enforce this ordering constraint. As you can see, we didn't really need to change a lot about our code to make that work. Anyway. Now, suppose you wanted to call that. We don't have the function traits in place here, so we need to explicitly specify the type list. But we just do that, call it on a command block object, and pass in a handler, which I creatively call do stuff in this case, which just prints hello world and prints the values it was given. So in this case, it's the same as do read file, just with a single 64-bit value parameter. Now, if we actually compile this, we will need to use C++ 17. And luckily, it actually compiles. I didn't touch this code since the last presentation, but I was still concerned it might not compile for whatever reason. And if we run that, we see, yeah, our handler just gets called just fine, and it decodes these kind of values just from the buffer, which is interesting because from looking at the buffer, you might not have guessed exactly how they kind of belong together, but our glue just magically takes care of it, which is nice. Right. So that was the kind of mini demo that I had in mind. And this is kind of, what is my PC doing? Don't quite appreciate that right now. There we go. So this demo quite quickly aside, there's still one thing I owe you, which is the encoding process for the response parameter block. But ultimately, that's the same kind of thing. You have a function called encode entry, which for a single type encodes the value to the buffer. And you have another function called encode all, which iterates over the entire command buffer, or rather over the entire response type list, and creates a response buffer based on these values. Now, we can't use parameter pack expansion for that, well, at least not easily, but we can use fold expressions, and these work similarly. If you haven't heard about them yet, I suggest you look them up because they're a really, really powerful feature, just like parameter pack expansions, just with the added twist that you can actually combine the values with a operator. In this case, we use the comma operator in C++, the purpose of which is somewhat unknown, but what it does is that it takes the expression on the left, evaluates it, and then moves on to the expression on the right. In other words, it strictly runs the expressions from left to right in sequence. which is precisely what we want here. We want to encode from left to right. That's kind of an evil hack, but at some point you just get used to it, I guess. Ultimately, it gets the job done, and it's a well-known pattern for those who have seen it. And if you want to use this in production, well, just add a comment about it and say, hey, fold over comma, this strictly serializes things, and that's just fine as well. Now, if you want to put things together, I promised you this very convenient small one-liner. You can always see it's not that big. We basically want a template function that takes the handler function and the command block. Well, at the beginning, we do the request header reading to make sure that the number of given parameters actually match what's expected by the function. And then we use our function traits to get a request list and a response list. Once we get that, we can do the verification logic. I omitted that in this case. But we can also just call the decode all and apply function that I just shown you on the previous slides. You can see applying this is really, really easy, actually. The implementation was kind of verbose at some point, but calling is just a one-liner again. We can then, once we get the results back from the command handler, build some sort of response header. Again, this is omitted, but it's relatively easy and just boring, kind of. And then we use the encode all function to write the actual results back to the command buffer. Right. So omitted for now is the verification and the build response header, but this is really the gist of it. Really all the interesting stuff in one slide. And again, it can be used for all the IPC commands. So we don't just need to call this with do read file and then need to come up with other logic for do open file, but actually we can really just do similar one-liners for do open file, do read file, and do close file, and all the others. Right. So this closes the chapter about what I call reflective generators, because it kind of combines the concept of reflection with generators and chains them together to actually do what we want. I found another approach quite interesting and useful, which is what I call declarative generators. We're kind of running short of time, but I'm hoping I can give you a quick overview about what I mean with that. And ultimately, this boils down to a more explicit approach of doing things. Right, a more explicit approach, and the point is it substitutes this kind of reflection process in the first place. So we get our type list not from reflection anymore, but from what I call a declarative interface. And this is a more explicit approach than what we've seen before, where we might have a namespace where we put all of our file system-related commands in, and we add new types describing each IPC command in our system. So we might have one type called open file, which has this kind of IPC command type, but it encodes the command ID right in the type itself. But this is not the only thing we care about. What we also care about is we care how many regular value type based parameters it takes. So in this case, it might take some sort of flags, file attributes, and I believe this is a file size or a path size or something. Anyway, so it takes a number of value-based types, and it takes some sort of special types, in this case a static buffer, whatever that means, it's a platform-specific thing. And it might respond with a file descriptor of the open file to the application. So this is a very different style than what we've seen before, but ultimately it captures all of the information we wanted. Again, really just on one single entity that we can operate on. Now we might do the same for something like get file size. Again, we have a different command with a different ID, different normal parameter list, different special, an empty special parameter list, and a different response list. And you can see how this might cascade into lots of large groups of IPC commands. Worth noting, this is kind of similar to the build-up pattern in OOP, where instead of having one big constructor, we have member functions that kind of initialize each member one by one, and you chain the function calls together like that. Just that this is on the type system level, so it's all compile time, so to speak. Kind of rushing through this right now. Now the idea, how you would define these things is basically you start with this template structure, and it gets just one parameter, which is the command ID, and just encodes that directly as a member, so externally it's visible again. And then your open file function becomes this. But well, then you want to add more. Well, you can do the same for get file size. Then you want to add more information. So what you do is you add a nested struct. You don't do this for any particular reason other than for enabling this kind of syntax. So this is the member lookup operator, so to speak. Well, nested type lookup operator. And just for the sake of enabling this kind of syntax, we need to use nested structs here. So we add more information by having a type list for the normal parameters here, and again, export them in the deepest scope. Well, if you want to add more information, we just nest another struct, and you can see where this is going. You basically just tag on more information as you go along the way. Right, and this is a very different approach than the reflection we've seen before. But oh well, you can similarly just, oh yeah, and the point is basically you have these type defs, and if you want to access any particular property, you just take this type open file, well, and look up the command ID value, for instance, in it, and you just get what you want. You can see that this is not too different in terms of the generators, though. In the generators, we get a slightly different signature. We now need to explicitly specify the IPC request. And we obviously don't use any function traits anymore. But we can actually conveniently verify the request header, because we can just have some sort of request. We can basically statically build the request header as part of the structure. And then we have a similar decode all and apply function. Well, no, it's actually the same decode all and apply function that I've shown you before, because you can just, again, take the request list from this kind of type def of the read file thing from before. Again, you just write the response similarly, etc., etc. So ultimately, the generator part is not all that different. It's just the way we got the type lists originally from and how we built the command header. Right. So at this point, you will be asking yourself, okay, what is this actually good for? To quickly wrap this up, well, what is this good for? We can take this declarative interface and we can write this glue handler function again, as shown before. It's called differently, but it's the same thing. We can use it like that, just like before. But we can do entirely different things now with this. We are not bound to actually handling things. We can actually synthesize IPC commands. We can go ahead and say, I want to write some testing code, which needs to run on my actual Nintendo 3DS. So if I want to do that, I actually need to start building command requests all of a sudden now and have some sort of convenient wrapper that builds this command header, calls the system call that sends off IPC commands. You can see there's also quite a lot of work to do. And it needs to read the response header and again turn it into something that my testing code can actually handle in C++ code, rather than in each test having some sort of decoding logic for the response again. So the synthesis can just be easily be done. We can just write a different generator called craft block that takes the declarative interface and does all of this logic for us. And well, in this case, I return a command block. It could just actually trigger the system call and return the results. Similarly, you could have a logging backend that takes the logging backend, which personally I use, for instance, in my kernel implementation, where when I encounter IPC commands, I look at the header. And then I have this very huge database of declarative interfaces like this. I go through all of them, I find one that actually matches. So I can tell just from these bits and bytes, which don't actually have this kind of information per se, like only the actual microservice will know which command it is. But because the kernel has this database, it actually also knows, even on the actual system it doesn't. Point being, and the kernel can just automatically log all of these commands and their parameter lists, rather than just printing out the raw command block and stitching this together manually. So that is really, really powerful. And this is really the core strength of this declarative interface approach. It's reusable among many, many different contexts, and you're not bound to one specific purpose. Especially because you can start gradually. You can hand tune all of your code for the handler part. Then once you decide to write a new kind of piece of functionality, well, all you need to do is write a new backend, new generator, sorry. And it's just a really nice separation of concerns, so to speak. And that is really the power of this declarative approach and declarative style programming in general, because it decouples logic from structure or data from control flow, whatever way you want to look at it. It decouples things that allows you to centrally define the structure of your IPC commands and handle the actual things you do with them separately. Yeah, you can look at the slide. You know, there's flexibility, consistency, separation, stuff like that. There are some drawbacks. There's a redundancy. You still need to write your handler function now. So there's an overlap in terms of things you define. However, I would like to contrast this from boilerplate. I would call it redundant, but I wouldn't call it boilerplate for the reason that consistency is ensured. So whatever you do, there is no room for typos. It's more work for you to type things out. But if you type them wrong, the compiler will complain about you because everything needs to be consistent and it's checked statically at compile time. But yeah, it's not quite as automated as we would hope it would be. And another corner is the implementation complexity, which is slightly higher than in the reflection thing. You have no way to gauge this right now, but if you see the implementation, it will be slightly more complex. But well, that's just the price you have to pay for the flexibility. But yeah, common to both approaches is you have no boilerplate, and it's type safe and correct by design, which is really, really nice, and ultimately what we were aiming for. Well, I meant to show a small mini demo for this. Well, don't quite have time for this. But basically, in my project, I really have these separate header files where I have huge databases of these commands. Each command gets its own declarative interface. That's also quite useful for documentation purposes. I meant to show this off, but I'm running out of time. I was meant to do a quick digression on node and performance, but the bottom line is it's fast. We're just doing compile time operations on type lists. So really, it's as efficient as if you had written all the code by hand, because compiler writers would actually have to go out of their way to generate code that is less efficient than what you've written. So it's really reassuring that you can write these things, you can build powerful abstractions, and even in resource constrained or timing critical environment, this will just work because it just compiles to optimal assembly. Right, to conclude, we've seen how untyped data makes serialization centric to emulation in various different problems domains, but also in inter-process communication specifically. We've seen how generators help us to get rid of all of this boilerplate and automatically turn lists of types into the runtime code that we actually want in this case. Forward expressions are quite big for this, and parameter banks especially as well, to reduce complexity and just write complex expressions really concisely. And to get type lists, we have two approaches. The first one being reflection, which just synthesizes the type lists directly from function signatures in our case. I'm really hoping that C++ 20 or 23 will get more extensive reflection capabilities, because then we could start, writing C++ structures and reflecting on them and do really all kinds of useful things on these. So I'm really looking forward to any progress on that area. And we've seen the declarative interfaces, which are an alternative to that, which allow maximizing your reuse because you can write very generic definitions but have different generators for different purposes. Right, and ultimately, the bottom line of all of this is you get a vastly more maintainable and more expressive solution that requires no boilerhead, and all of that at basically zero performance overhead. So hopefully you'll be able to take some lessons away from this. That's all I have to say, really. If there are any questions, feel free to come up to me later after the talk, because I'm afraid we don't have any time anymore. But so far, thanks for your attention.
Evaluation, couldn't you just put it all in a tuple with a comma fold and then just use std apply, something like that?
Yeah.
That will give you.
That's actually what I did before. Then I talked to Gaspar actually about it.